Right, hello grade 12s. This is your second lesson for Wednesday the 18th of March. Specifically, it's a brand new chapter. It's under paper 1, so we're back to our paper 1 book, and it falls under algebra. And the chapter is called Polynomials. That's in your classroom mathematics textbook. And specifically today we're going to talk about polynomial division. Now I just want to start off, when I start with this chapter, I always say to people, this chapter in its own is really not that important. They hardly ever assess these things. So you'll see when you start working through past exam papers, they don't actually ask you polynomial division in a paper. That's not the point. The point is, this is almost like a plug-in for the next chapter. And the next chapter is super important, that's calculus. So you need this polynomial division, and you need the whole idea of polynomials for the next chapter. So don't get too stressed if you're not very good at polynomial division. That is not the point of this chapter. So I will again go, and at the end I will very clearly state this is what you need from this chapter. So please work through it, try and understand it, but don't have a complete breakdown if you go, this is too difficult, I'm not going to be able to do this. Because no, they don't go and assess this in a paper per se. It's a plug-in for calculus. So concentrate, but don't get stressed out. Now, in order to understand polynomial division, we first have to look like a very simple example like 45 divided by 7. Now, if you look at 45 divided by 7, lots of you guys are so used to the way we do it, which is to simply grab your calculator, type in 45 divided by 7, and then you end up with 45 over 7, and if I go to 2 decimal places, you press this button, and then you end up with 6,42857. Now, before you did this, back when you were in primary school, you would go and say, okay, I could take 45, and I can divide that by 7. Then I can split this up and I can say, okay, but what's the closest multiple of 7 to 45? And the closest multiple of 7 to 45 is 42. So I can split up that 45 into 42 plus 3, and then I can divide that by 7. But now, because there's a distributive law, I can go and say it's 42 divided by 7 plus 3 divided by 7. And then, because this is a multiple, which is the way I planned it, 42 divided by 7 is 6 plus 3 over 7. So this is, again, it's just to remind you guys that before you had that whole idea of dividing and getting it to decimals, you went and in primary school you said it's 45 divided by 7 is 6 remainder 3. So what I've got here is I've got the fact that there are 6 multiples of 7 in that 45, but then there's 3 that is not a multiple of 7, so that's going to be my remainder. So I say it's 6 and then remainder 3. Now what this allows me to do is this allows me to now go and say that 45 divided by 7 is equal to 6 plus 3 over 7. And if I multiply the entire thing by 7, so let me just rewrite so you can understand it a little bit better. Then I can go and say multiply all of the terms by 7. So 45 over 7 times 7 is 45. Then this is going to be 6 times 7, and I'm going to leave it like that, 6 times 7 plus, and this is then going to be 3, because 3 over 7 times 7 gives me 3. So what I have to understand there is I have to understand 45 can be written out as 45 is equal to 6, which was the answer, that was the quotient, times 7, that is the divisor. So this is my quotient, that was my answer. This was my divisor, and this was my remainder. So you can actually write any number out as a product of its quotient and its divisor plus its remainder. So I'm going to refer back to this. I know you look at it and you go, why would I want to do this? There's a very good reason why I showed you this, because once we start doing this with the polynomials, the algebra, we need to come back to this and refer to this, so it's going to be easier to understand. So please just remember, if I go 45 divided by 7, I get a result of 6 plus a remainder of 3, which remains over that divisor. And then if I fix it up, I can write it as 45 is equal to my answer, my quotient, times my divisor 7 plus 3, my remainder. Okay, so just remember that for the next example. So in the next example, suddenly we have something like this. And if you think about this, this looks a lot like the end result we had over here, which states that a number is equal to a quotient times the divisor plus 3. So if I compare that to this one, I'm saying a certain polynomial will be equal to a quotient, and this could be the quotient or that could be the quotient, it really doesn't matter. So it's a quotient times a divisor, or a quotient times a divisor plus a remainder. So this one, because it looks a lot like this final result, I now need to go and find out what was the actual polynomial that this was before I broke it up. So we're just quickly going to look at this so that you can then understand when I have an answer and I break it up again, you can understand where this comes from. So we'll just multiply this out and we will say it's going to be x times x squared, which is x cubed, and then x times negative 3x, which is negative 3x squared, and then x times 1, which is plus x, minus 2x squared plus 6x minus 2. And then I'm just going to bring down that plus 5. So I'm really hoping I didn't make a mistake. I normally have a bunch of kids in my class telling me, ma'am, you made a mistake. So I'm going to have to now just make sure that I haven't done anything, because if I did make a mistake, I can almost in my head hear you guys saying I've made a mistake. So there is the x cubed, there's the minus 3x squared, the plus x, minus 2x squared, plus 6x, minus 2, plus 5. So it seems that that is correct. Now if I just add the like terms, x cubed, and that's going to be minus 5x squared, plus 7x, and then minus 2 plus 5 is plus 3. Then what we are saying is we are saying, therefore, this polynomial, and that's a polynomial expression, x cubed minus 5x squared plus 7x plus 3, can be written out as a divisor times a quotient, or this could have been the divisor and this could have been the quotient. So divisor times quotient, or this could have been divisor times quotient, it really doesn't matter. Plus then a remainder of 5. So I was just showing you that because if we multiply this one out, we get to this, then I can rewrite this one as that. But now if I go slightly back one, I can then decide my actual divisor here was that x minus 2. So I can now divide this side by x minus 2, and I can divide this side by x minus 2 as well. Now the reason I want to do that is to help you with the next section where we're actually going to be doing these divising sums, or division sums I should rather say. But you can then go and you can say, if I were to divide this polynomial by that polynomial, then the end result should be the following. I should be able to go and say, because there's a plus over there, I can use my distributive law and I can say it's the first term divided by that plus the second term divided by that. So if I take that first term, x minus 2 times x squared minus 3x plus 1, and I put that over x minus 2, plus then that second term, 5, and I put that over x minus 2. Over here, I can divide away the common factor, and then I can rewrite it out as this. So I can say, if I take this polynomial divided by this polynomial, that's my result. That's my result. Which again, I'm going to refer back to this one when we do the next example, which is the actual polynomial division. Currently, all that we're really doing is we're playing with expressions. We're saying expressions can be broken up in this manner. By the way, it's a very formal name. It's called the Euclidean property, but again, if you forget it, it's really not a problem because they don't actually assess the Euclidean property. So what we are trying to get to in this particular exercise is we are trying to get to these types, where we say a polynomial divided by a polynomial. Now, the moment I divide this polynomial by that polynomial, I then want to get a quotient plus a remainder. That's the whole idea. So I'm going back to this idea that if I divide a polynomial by a polynomial, I should end up with a quotient plus a remainder, and that remainder is still stuck on that divisor. Now, in order to do this, there's a specific technique which is called long division. Now, I'm going to show you long division, and long division is very annoying. I don't like it. I will show it to you guys, and then after I've shown you long division, I will show you a little shorthand technique that is actually, in my mind, slightly easier, but I do know some people prefer the long division. So let's look at the long division. Now, long division is something you did centuries ago when you guys were in primary school. X squared minus 2x plus 2 divided by x plus 3. And when you did this, like in primary school, obviously you didn't do complicated ones like this. We'll go back to that first example that we had, which was the 45 divided by 7. So if I had to go and say 45 divided by 7, you guys would have gone and said 7 can't go into 4. But 7 goes into 45 6 times. And then you guys said, okay, 6 times 7 is equal to 42. And you did that specifically so you could find the remainder. And then you said 45 minus 42 is equal to 3. So what did you say? You said 45 divided by 7 is 6, remainder 3. That's the idea we're going for. Now, I know this is a long method. You guys didn't use the long method, but we need the long method specifically over here. So again, we look at this and we say, x plus 3. I can't ask x plus 3 goes into that whole thing. So I will only focus on the following. I will only focus on how many times does x go into x squared. So that's my first concern. X goes into x squared x times. And then I go and I say x times x over here is going to be x squared. But, hey, there's not only x, there's a 3. So not only must I times x by x to get that x squared, I must also times by that 3. So I say x times x is x squared, and I say x times 3 is 3x, and I put it over there. Now, if you compare this example to this one, I had to subtract to find the remainder. So I'm going to do the exact same thing here. I'm going to put a bracket around this, and I'm going to go and subtract it to find the remainder. So clearly, x squared minus x squared is 0. I'm not going to put a 0 there. I know this is 0. But then, to find the remainder over here, I say it's minus 2x minus 3x. Please remember that minus must be used distributively. So I'm not just subtracting this one, I'm also subtracting that one. So minus 2x minus 3x is going to give me minus 5x. That's my remainder. Now, normally over here I'm done. And the reason I'm done over there is because 7 can't go into 3, so I'm done. But over here, can x go into minus 5x? Yes, it can. So I'm not done over here. So now what we're going to do is we're again going to go and just look at these two. I'm again going to look at the x, and I'm going to look at that minus 5x. And I'm going to ask myself, how many times does x go into minus 5x? And I'm going to put it up here, minus 5 times. And then you say, again, multiply. So I'm going to do this multiplication, but now obviously I'm going to multiply there, and I'm going to multiply by that one over there. Sorry, it's getting a bit messy, but you get the idea. Hopefully you get the idea. 5 times x is then going to be equal to, minus 5 times x is then equal to minus 5x. And then you say minus 5 times 3 is then equal to minus 15. Now you should notice I'm going to subtract these two, but there's nothing there to subtract the minus 15 from. That's not a problem. I'm going to bring this 2 down. Now again, exactly the same principle. Put a bracket around, put a minus in front, and now say minus 5x minus minus 5x, which is then plus 5x, this is 0. Then over here, 2 minus minus 15 becomes 2 plus 15, which is 17. Now I'm done. So now I can go and I can say, because x can't divide into 17, this is then going to be my remainder. So you need to understand, this particular specifically was my polynomial. This was my divisor. This is now my quotient, and this is my remainder. So looking back at those previous ones, what I can say is I can say, therefore, x squared minus 2x plus 2 divided by that x plus 3 is then equal to my quotient, my answer, x minus 5, plus my remainder, 17, and that remainder stays on that x plus 3 right there. So this is what I'm doing. I'm breaking this up, saying that divided by that is equal to my quotient plus my remainder. And then the other thing I can do is I can rewrite it, and the way I can rewrite it is I can say, if I multiply all of this by x plus 3, then this one, if I multiply by x plus 3, becomes x squared minus 2x plus 2. This one will be x minus 5 times x plus 3. And this one, if I multiply by the x plus 3, is just going to be plus 17. So now I'm back to what I had in that previous one. And what I had in that previous one was specifically that whole idea that you can go and you can rewrite any number specifically, or not any number, any polynomial in this case, as a product of the divisor times the quotient plus the remainder. So this is exactly what I've got over here. I now can rewrite this particular one as a product of its divisor times its quotient, right there, plus its remainder. And again, this is called the Euclidean property. Not that important, useful skill to have, but really people, this is just going to serve as a plug-in later on. So you can look through this, you can try the examples, but if you get horribly stuck, it's really not a train smash. Now, in the next example that I'm going to do will be a next video, because this video is getting a little bit long. I'm going to actually show you a nice little trick to do this long division in what I consider to be an easier way. But some people might say, no, I prefer this long division. That's up to you if you prefer it. But I will show one last worked example in that last little video done in a different way, which you might actually prefer.